In this topic, we will discuss projections on Hilbert space H. So we already know that projections on a Banach space, they are just idempotent operator on B. Let us see B is a Banach space, then projection P on Banach space B. This is operator P with the property that P square is equal to P. Now in this section we will find out the projections on Hilbert space, or we can say how the projections behave on Hilbert spaces. So we already know that if we have a projection P, then we can determine two closed linear subspaces M and N. M is range space of P and N is null space of P, such that B can be written as direct sum of M and N. And also conversely, if we have a pair, let us say M and N, of closed linear subspaces, then we can determine a projection P whose range space is M and null space is N. That means there is 1-1 correspondence between the projections on a Banach space and a pair of closed linear subspaces of that projection, which gives the direct sum of B. And one of them is the range space of the projection and other is null space of the projection, and these two spaces, they span the whole space and they have only zero vector in common, because they give a direct sum of the space B. But in case of Hilbert spaces, the structure of projections, that gives some additional information. So firstly we have this theorem A about projections. Now this theorem says if P is projection on H with range space M and a null space N, then M and N, they are orthogonal to each other if and only if P is self-adjoint. So P is projection on H, where H is Hilbert space, with range M and null space N. Then M is orthogonal to N if and only if P is self-adjoint, which means P star is P. P adjoint of P is equal to P. And also in this case, the null space N is just M per. It is just perpendicular of M. So now we know, since P is a projection whose range space is M and null space is N, that means the whole space H is written as direct sum of M and N. That means every vector Z in H, that is just can be written as sum of the vectors X and Y in M, and this sum is unique representation of Z. So every vector Z in H can be written uniquely as X plus Y, where X is in M and Y is in N. Now we have to prove this if M is perpendicular to N, if and only if P is self-adjoint. So firstly we assume M is perpendicular to N. So if M is perpendicular to N, since X belongs to M and Y belongs to N, so X is orthogonal to Y. Now we have to prove P is self-adjoint. That means we have to prove P star is equal to P. So for that we will prove actually P star at Z is for that we will prove this thing, P star Z with Z is equal to PZ with Z for all Z in H. So firstly we take the left hand side, P star Z Z. So this P star becomes PZ by the relation of an operator and its adjoint. So since P is projection whose range space is M, so PZ will be X, because Z is X plus Y, so PZ will be X. So Z can be written as X plus Y X, So this is the inner product of xx and yx. Now we are assuming x is perpendicular to y, so this inner product yx, this is 0, so this becomes just xx. Now we start with this right hand side, pzz. So pzz is equal to xz, because the value of pz is x, so it will be x plus y, it is xx plus xy. Again x and y are orthogonal to each other, so it is just xx. So from these two we can say p star z, this is pzz for all z, which means p star minus p z, this is 0 for all z, and therefore p star minus p is 0 operator, so p star p is equal to p, that is p is self-adjoint. So now we will prove the converse part. Conversely, if p is self-adjoint, then we have to prove m is orthogonal to n. That means we have to prove for any x in m and for any y in n, x and y are orthogonal. So let x be any vector in m and y be any vector in m. We want to prove x, y inner product is 0. So this x can be written as px, because whenever x belongs to m, since the range space of p is m, so px is just x. So this becomes x p star y. Now because p is self-adjoint, that is p star is equal to p, so this p star becomes just p, and py is 0 because the null space of p is n and y belongs to n, so this is just x0, so this is 0. So we have proved here x is perpendicular to y for all x in m and for all y in n, therefore m is orthogonal to n. So from this we can say a projection on a Hilbert space whose range space is m and null space is n. This is in this setup, range space and null space are orthogonal to each other if and only if p star is equal to p. So the remaining part to prove in this theorem is n is equal to m perp. Now we know m is perpendicular to n. So now we will prove here n is just m perp, means the null space is just the m perp space. So because every vector of n is perpendicular to every vector of m, so n is contained in m perp, because for each y in n, y is perpendicular to x for each x in n, so that means n is contained in m perp. Now we want to prove equality, n is equal to m perp. So let us suppose that n is a proper subset of m perp. So if n is proper subset of m perp, then since M is proper closed linear subspace, and since for the Hilbert space H, M perp is closed linear subspace, so this is also Hilbert space, because a closed linear subspace of a Hilbert space is Hilbert space. So M perp is closed linear subspace, and since n is proper subset, so there exists a non-zero vector in M perp which is perpendicular to n. Then because then n is proper subset of closed linear subspace of Hilbert space M perp, so there exists a non-zero vector, let us say z0, in M perp such that z0 is perpendicular to n. Now z0 belongs to M perp, so z0 is perpendicular to M also, and z0 perpendicular to n. But we know M and n, they have only zero vector in common, since H is the direct sum of M and n. Now also, since H is direct sum of M and N, therefore Z naught is perpendicular to H, because if it is perpendicular to M and N both and H is direct sum, so it is perpendicular to H. So it means this thing is impossible, because there does not exist any non-zero vector which is perpendicular to the whole of the space. So that is a contradiction. So it means N cannot be a proper subset, it will be equal to M perp. So in this theorem we have proved that M is perpendicular to N if and only if P star is equal to P. That means it is self-adjoint operator. So these type of operators whose range and null space are orthogonal, they are called perpendicular projections. The projections whose range space and null space are orthogonal to each other, they are called perpendicular projections. In case of Banach spaces, we consider the projections are operators which are idempotent, which means which satisfy the property P square is equal to P. But in case of Hilbert spaces, we refer to the perpendicular projections as projections, which means in Hilbert spaces the projections which are perpendicular the projections for which projections are those operators for which the range space and null space are always perpendicular. That means projection on Hilbert space can be defined in this manner, that projection on a Hilbert space is an operator which is idempotent and which is self-adjoint, which means which satisfies the property P square is equal to P as well as P star is equal to P. So we will consider the projections on Hilbert space H are those operators for which P square is equal to P and P star is equal to P. So we have zero and identity operator. They are always projections on Hilbert space, because 0 square is equal to 0 and 0 star is equal to 0. Similarly for the identity operator. So for example, 0 and I are projections on H. And obviously they are distinct projections if H is non-zero, because if H is 0, then they are same projections which maps the space 0 to 0. But if H is non-zero, they are distinct projections. Now we know there is 1-1 correspondence between the projection and the closed linear subspaces. In case of Banach spaces, we take M and N, where M is range space and N is null space. But in case of Hilbert spaces, we have proved in this theorem that if P is a projection on Hilbert space H, then its range space is M and its null space is M perp. So there is 1-1 correspondence between the projection P and the range space M, or we can say the pair M and M perp, where M is range space and M perp is null space. So to each projection P, there corresponds to each projection P, there corresponds a range space, or you can say its range space M, and M consists of all the vectors of this type Px for any x in H. Now this M is a closed linear subspace. M is closed linear subspace of H. And conversely, if we have a closed linear subspace, if M is closed linear subspace of H, then it corresponds the projection P whose range space is M and which is defined by P of x plus y is x, where x belongs to M and y belongs to M perp. Now whenever we have M is closed linear subspace of H, we have M perp space, and we take any x in M and y in M perp and we define P x plus y is equal to x, then this P will be projection on H whose range space is M. So P is a projection with range M, and this P is the projection. We will speak this P as the projection on M. So now it is clear that if P is projection on M, then I minus P is projection on M perp. So one more thing we can note here: if P is projection on M, then I minus P, this is projection on M perp. This we have done in Banach spaces also. If P is projection on M, then I minus P is projection on N, and the converse also true, and converse also holds. If I minus P is projection on M perp, then P is projection on M. Now we have one more result which gives three equivalent conditions for the projections. So we have this result, or we can remark it. If P is projection on M, then the following conditions are equivalent. Number one, x belongs to M, and secondly Px is equal to x, and third is norm Px is equal to norm x. Or we can say if P is projection on M and x belongs to M, then these conditions are true. Px is equal to x and norm Px is equal to x. So equivalence of first two conditions, that is obviously by definition of projection, because if x belongs to M and M is range space, because we are saying P is projection on M, that means P is a projection with range space M. So if x belongs to M, then Px is equal to x, because Px can be written as P of x plus 0, and that will be just x. Similarly, if Px is equal to x, then it will be projection on M and x belongs to M, because if Px is equal to x and range space of P is M, that means Px belongs to M, that means x belongs to M. So first two are obviously equivalent, one if and only if two they are. This is obvious. Now 2 implies 3, that is also obvious, because if two vectors are same, then their norms are same. If Px is equal to x, then their norms are obviously same. But we cannot say if the norms of two vectors are same, then the vectors are also same. So we will prove here 3 implies 2. So now we are given with norm of Px is equal to norm of x, but we have to prove Px is equal to x. We start with this. For every x in H, for every x in the Hilbert space H, we start with norm of x square. So norm of x square can be written as norm of ix square, and norm of ix square can be written as px plus I minus px. So we are adding px and subtracting px in this step, and we know px and I minus px, they belong to the orthogonal spaces. Px belongs to M and I minus px belongs to the M perp space, because we have written earlier that if P is projection on M, then I minus P is projection on M perp. That means these two vectors are orthogonal to each other. So we will apply here the result that if two vectors are orthogonal to each other, then norm of square of norm of sum is equal to just norm of this square plus norm of this, which means Pythagorean triangle. Pythagorean theorem says if two vectors are orthogonal, let us say x and y, if x and y are orthogonal to each other, then norm of x plus y square is equal to norm x square plus norm y square. So we will apply that result because we know this and this vector, they are orthogonal to each other. So this will become just this. Now if we assume norm of px is equal to norm x, because we want to prove 3 implies 2. So if norm of px is equal to norm x, then norm of px square is equal to norm x square. So this will be cancelled with this, because we have written here norm of x square is equal to this plus this, but these two are equal, so this will be cancelled. So this means this is 0. Now since norm of px is equal to norm x, which means norm px square is equal to norm x square, which means norm of this is 0. So this means I minus px is 0, because norm of something is 0 if and only if that vector is 0. So I minus px is 0 means px is equal to x. So this proves the condition 2. Now one more thing we have to note about these projections, that if P is a projection on Hilbert space H, then P is an operator which lies between 0 and I operator. So if P is projection on H, then P is lying between 0 and I, which means P is positive operator, but it is less than equals to I. From this relation, norm of x square is equal to norm of px square plus norm of I minus px square, we can say this is greater than equals to norm px square, because norm of anything is non-negative, so we can write norm of x square is greater than equals to this. So it means norm of px is less than equals to norm x for all x. Now if norm of px is less than equals to norm x for all x, that means we can say norm of p is less than equals to 1. And secondly, if x is any vector in H, then what is pxx? This is, because x is a vector in H, then px is in its range space. If this vector belongs to range space, then it is equal to p of px, because any vector which is in the range space of the projection, for that vector is equal to p of that vector. So we can write px as p of px. Then it is px, p star x, because this p becomes p star here. Now because this is projection on Hilbert space, so we know p star is equal to p. So this is just px. Now px is just norm of px square. So this is greater than equals to 0. So we have proved here pxx is greater than equals to 0. That means it is a positive operator. Therefore p is positive operator, or we can say p is greater than equals to 0. So we say p is greater than equals to 0 because we have defined earlier a relation, partial order for the operators, in this sense that if pxx is greater than something, then p is greater than that. Now we have proved here that if p is any operator, then p is greater than equals to 0. That means it is positive. If p is projection, we have proved if p is projection on some space M, then p is greater than equals to 0. Now we know if p is projection, then I minus p is also projection. That means I minus p is also positive. Also I minus p is projection. Therefore I minus p is positive operator. So if I minus p is positive operator, then p is less than equals to I. So from these two we can say p is operator lying between 0 and I. So it is positive operator which is less than equals to I. P less than equals to I, it means that inner product, that this thing pxx this is less than equal to xx. Pxx is less than equal to Ixx, and Ixx is just xx.